Good afternoon, students. In the previous class we have seen the design of the pavements with geosynthetics, and let us continue the same topic in today's lecture. A brief outline of today's lecture is we will have a recap of the previous lecture, then we will work out some numerical examples to illustrate whatever we have discussed in the previous class, and we will see how the geosynthetics are applied in pavements for different to overcome different problems, and then we will briefly look at some construction aspects. We have seen that in the previous class that the entire design of flexible pavements is based on the California bearing ratio or the CBR of the subgrade, and this particular table gives some guidelines on how to interpret some field observations for the CBR values, because many times we go to the field, we may not even have time to collect a soil sample, bring it to the lab and do the testing. And just as an approximate guide, if we collect a soil sample in a tube and if we are able to easily penetrate our thumb, we can say that the CBR of that particular soil is less than 2, and if we have to exert some moderate pressure to penetrate our thumb, the CBR value could be anywhere in the range of 2 to 3, and when we try to penetrate our thumb, we are able to make only a small indentation, the CBR value could be anywhere from 3 to 6, and say we are not able to indent with the thumb, but using the nail, if we are able to indent it, the CBR value could be anywhere from 6 to 16, and if we are able to indent even with a thumbnail, the CBR value could be greater than 16. So, this table gives us some way of identifying the CBR value of the soil that we come across in the site, and this particular formula we have seen in the previous class. This was adapted by Giraud and Noire based on the data from US Army Corps of Engineers, and this particular formula is valid only for the number of passes less than 10,000, and this is a generalized formula because we can consider any axial load P and any rut depth R, and then the soil cohesive strength, the Cu undrained cohesive strength, because the previous formulas that we have seen in the earlier class, that they are very particular for a standard axial load of 80 kilonewtons and then a rut depth of 75 millimeters, and here the H naught prime is the base course thickness under given number of traffic repetitions, this is in meters, and capital N is the number of traffic passes, P is the axial load in newtons, R is the rut depth in meters, and the Cu is the undrained cohesive strength in pascals. And we have seen in the previous class that approximately 1 CBR is equal to 30 kilopascals or 30,000 pascals, and the Cu is approximately equal to the CBR value times 30 in terms of kilopascals. And now let us look at some numerical example and how to apply this equation, because it is a combined equation that gives us the influence of the number of traffic passes N, and then the axial loads P, the rut depth R, and the Cu, the effect of all these factors on the pavement thickness. And let us say that we have a axial load of 80,000 newtons and allowable rut depth of 0.3 meters, and the Cu is 30 kPa or 30,000 pascals, and the number of passes 1000 and 10,000, and in the case of 1000 passes, if we substitute all the values, the pavement thickness comes out as 0.46, and let us say that in the second example we keep all other parameters the same except that we increase the number of passes to 10,000, and now our base thickness increases to 0.64 meters. Earlier it was 0.46 meters. So now let us look at the different combinations and directly compare one against the other. Let us take the very low number of passes 1000, axial load of 80,000 newtons, rut depth of 0.3 and the Cu of 30 kPa or 30,000 pascals. The thickness required is 0.46, and when we increase the number of passes to 10,000, the rut depth the thickness of the pavement increases to 0.64, and now let us keep the same number of passes as 10,000 and the axial load of 80,000, but decrease the rut depth, allowable rut depth to 0.075 and the Cu of 30,000 pascals. The thickness of the pavement increases to 0.73. So that means that if we have a lower tolerable rut depth, we need to provide a thicker granular base, so that our combined stiffness is higher, that results in lesser rut. And the influence of the Cu, the increase of Cu to 60,000 pascals is to reduce the thickness. So now the thickness has reduced to 0.41 from earlier 0.64, and if we increase the axial load to 120,000 newtons, and while all other parameters are the same, the thickness of the pavement increases to 0.76 meters. So this particular equation that we have is actually, it is adapted by Giraud and Noire from the earlier publications of the US Army Corps of Engineers to express the effect of all the parameters on the thickness of this pavement, and this particular equation is only valid for unreinforced pavements. And for the case of a geosynthetic reinforcement, Giraud and Noire, they have worked out the solutions and given the thickness in terms of the CBR value on the x axis, and here we have two quantities h naught prime, that is the thickness of the unreinforced pavement for the case of standard axial load of 80 kilonewtons and the tire pressure of 480 kPa and a rut depth of 300 millimeters, and here the h naught is only dependent on the CBR value of the subgrade and then the number of load passes. The number of load passes are worked out in terms of 10, 100, 1000, 10,000. You see that everything is in terms of log scale, and so if you know the CBR value or the undrained cohesive strength of the soil, we can directly read off the thickness of the unreinforced pavement directly from this graph, and then the other quantity is the delta H, that is the possible reduction in the thickness of the pavement because of the placement of a geosynthetic layer, and the solutions are given for different secant modulus values, the E of 10 kilonewtons, 100 kilonewton per meter, 200, 300, 400, 450. So this directly we can read off the CBR value against this modulus. So we have totally 6 graphs, and we can directly read off this delta H. And now let us look at one small design example. Let us say that our number of load passes or the number of load repetitions is 10,000 and the standard axial load is 80 kilonewtons, and let us say that our CBR value of the subgrade is 1 and allowable rut depth is 0.3 meters, and modulus of the geosynthetic is given as 200 kilonewtons per meter, and the tire inflation pressure is 480, and from the chart for a CBR of 1, this should be 1 and n of 10,000, the thickness of the pavement for the unreinforced case comes out to approximately 0.57. So, this 1 and repetitions is 10,000. So, directly we can read off, and it comes to about 0.57, and then the reduction in the thickness because of the placement of reinforcement for a CBR of 1 and modulus of 200, this delta H comes to approximately 0.25. So, let us see, this CBR of 1 is here, and this the sorry, this this fourth graph, sorry, this fourth graph is corresponding to E of 200. So, this comes out to about approximately 0.25, and so we can say that because of the provision of the reinforcement, we can reduce the thickness of the pavement by 250 millimeters. So, the thickness of the granular base that is to be provided is only now reduced to 350 millimeters from the earlier 570 millimeters. So, it is a substantial saving, because this not only decreases the quantity of the natural materials, but also decreases our construction time, because we need to bring in this much lesser material. So, it is faster, and then the carbon footprint of the construction also reduces, because if we need to bring in any material, natural material, we need to spend in terms of the number of lorry passes and other things. So, this is these charts that we have, they are extremely useful, and the Koerner in 1999, he has proposed another method for incorporating the effect of reinforcement by taking in some empirical equation that was published by the US Army Corps of Engineers, and he called it as the CBR method of design. And here the H is the base layer thickness that is related to the number of load passes and other factors like this 3.24 log C, where C is the number of load passes plus 2.21 multiplied by the quantity in square root P by 36 CBR, where P is the equivalent single wheel load, and the CBR value either for unreinforced soil or reinforced soil, and A is the tire contact area divided by 2030, and this the CBR that we use is either the CBR of the unreinforced subgrade soil or the reinforcement with reinforcement, and we can perform a CBR test, a modified CBR test, by introducing a layer of geosynthetic at the interface between the aggregate and then our soil, and do the normal CBR test and interpret for the increased CBR value. And the units for all these quantities, the H is in millimeters, the P is in equivalent single wheel load, that is in newtons, the tire contact area is millimeter square, and the CBR values in terms of percent, either 1%, 1, 2%, 2, 3%, 3, and so on. And let us look at a simple example. Design the thickness of pavement for a soaked subgrade CBR value of 1, and number of load repetitions is 10,000, and the equivalent wheel load is 40 kilonewtons, and the tire contact area is 300 by 450 millimeters, and the CBR value from the modified test by introducing the reinforcement layer is 3. So, now we can substitute all the values in this equation for H, that is 3.24 times log of 10,000 plus 2.21 multiplied by 40,000, that is the wheel load in newtons, divided by 36 times CBR that is 36 times 1 minus 300 times 450, that is the tire contact area, divided by 2030, this whole quantity to the power of half, and this thickness comes to 490 millimeters. And now let us estimate the same thickness for the case of reinforcement. The CBR value is 3 when we introduce this layer of reinforcement, and this H prime comes to 265 millimeters, or in other words the reduction in the thickness is 225 millimeters. So, it is a substantial reduction in the thickness. So, by either using this modified equation or this design chart, we can estimate the thickness of the pavement for both unreinforced case and for the reinforced case. So, now let us see how we can employ the geosynthetics for improving the longevity of the pavements and reducing the thickness, and also making them durable for a longer time. So, these geosynthetics, they help us in several ways in the form of reinforcement. When we use a geosynthetic as a reinforcement layer, it helps in reducing the subgrade stresses and prevents the cracking of pavement due to the swelling of foundation soil. I will show you some examples later on in this lecture to illustrate how we can utilize the reinforcement not only in the case of a soft subgrade, but also in the case of stiff subgrades where the soil is subjected to swelling or the volume changes. And we can use a geosynthetic as a separator that prevents intermixing up of the materials in different layers, and as a filter layer to prevent piping phenomenon, and as a drainage layer to provide for safe disposal of water whatever enters our pavement, and as an asphalt reinforcement layer or as a paver reinforcement layer. It helps in preventing the reflection cracks. Koerner in 1999 in his textbook has very nicely summarized the function of different geosynthetics based on the CBR values. So, when the soaked CBR of the subgrade soil is greater than 3, we need a geosynthetic or a geotextile only as a separator. You may not require much for reinforcement function because the strength is sufficient, and when when the soaked CBR is in the range of 3 to 1, we need to use the geosynthetic not only as a separator, but also as a stabilizing unit or as a reinforcement layer. And for extremely soft soils with a CBR of less than 1, the soaked CBR of less than 1, we need both functions as a reinforcement or also as a separator. And now let us see how we can employ the geosynthetics for stabilizing roads and expansive clays. Well, how do we identify what is an expansive clay? See, we can identify them based on the liquid limit. Whenever we have a liquid limit of greater than 50%, we classify that soil as a clay of high plasticity, and we can expect the problems not only because of swelling during the winter season or during rainy season, and shrinkage during the dry season. And apart from the liquid limit, the shrinkage limit of less than 12% also indicates the swelling nature of the soil, and the other quantity that we have is the differential free swell index. Anything more than 50% can be classified as a highly problematic soil that may swell or shrink. And what are the different techniques that we have for stabilizing these soils? Traditionally, the lime mixing, directly mixing the lime with the subgrade soil, or by installation of lime columns or cement stabilization, that is we can use a cement to bind the soil particles together so that our swelling tendency is reduced, or we can use a soil reinforcement, or that is by providing some reinforcement layer we can suppress the swelling tendency. So, what happens when you have the swelling of the soil? This is what happens: the longitudinal crack and the pavements over constructed over expansive clays. We see this longitudinal crack is actually very wide. This is happening at the center of the road and also at the edges, and we can stabilize this type of soils by using a suitable biaxial type geogrids. The biaxial geogrid, as we know, these are the geogrids that have significant tensile strength in two directions, in both the directions, longitudinal direction and also in the transverse direction. And for this geogrid to have a good interaction with the soil, the percent open area should be greater than 70%, and then these geogrids, they should be able to develop high enough tensile load at a low enough strain. That means that their modulus should be in the range of 200 to 300 kilonewtons per meter or higher, and they should also have a good junction strength, because when the soil is trying to swell, it subjects the geogrid to very large tensile stresses, and if the junction is not strong enough, the geosynthetic or the geogrid might rupture at the junctions. And this is how we employ a geosynthetic. Let us say that we have a highly plastic clay soil as subgrade, and we have our base course, flexible base course, and below this we can provide a geosynthetic layer, and of course on top of our base course we provide an asphalt coating, and this particular material is from the paper that was published by Professor Johnberg and his student Gupta in 2009 at the International Soil Mechanics Conference. And the mechanism that they have proposed is like this for two cases, that is when the embankment shrinks during the dry season and when the embankment swells. So, this is what happens when the embankment soil shrinks, the volume reduces. So, originally our embankment, road embankment is shown by these dotted lines like this, and because of the shrinkage, our volume reduces, and the new configuration of the embankment is like this, and the likely locations of cracks are shown here, or the reverse may happen during the rainy season. There is a volume expansion. So, here the dotted line is the original configuration, and the solid line is the new configuration after the swelling, and once again we can have the tension cracks at these locations. So, these if we provide a reinforcement that can bind the soil together, we may have, or we could have a good performance. And in this paper, Johnberg and Gupta, they have presented the data on some field work that they have done in Texas. So, they have treated soil over a length of almost 3 kilometers. They have divided the stretch of road into 3 sections. In section actually section 1 with the reinforcement, and then section 2 with another type of reinforcement, then there is a middle section without any reinforcement, and so wherever they have provided the reinforcement, they did not find any longitudinal cracks, and where there was no reinforcement, they have provided they have seen the cracks. That means that the reinforcement that is provided is able to suppress the the volume change tendencies of the soil and keep the integrity of the pavement nicely. And in fact they have seen the effect of the junction strength of the geogrids. They have tested with the 2 types of geogrids, both having different strengths, and so they have seen that geosynthetic having a higher strength but having a low junction strength, it has shown some distress because the ribs have opened out at the junctions. So overall their conclusion is that the use of geogrids is a suitable solution to get a good performance of the pavements in the case of expansive soils. And let us now look at another application, that is in the case of repair of flexible roads. Actually this is what happens. So let us say that we have a road and the top surface after certain period of service it cracks up, and we place a new asphalt layer, and that also ends up with cracks. This is what happens. So we provide a relatively thin asphalt overlay on the existing pavements that may have some surface cracks in order to reduce the water intrusion into the pavement and reduce the surface roughness and improve skid resistance and increase the structural capacity, because this is frequently done as part of the maintenance. And when we are repairing, sometimes these old cracks, they may be filled or they may not be filled, and sometimes we notice that within a short time the cracks from the old pavement they propagate to the surface, and the new pavement also undergoes failure. And this process of the cracks spreading from the old pavement to the new overlay is called as the reflection cracking, and it is a very usual phenomenon that we see in most of the flexible pavements. And because of the reflection cracking phenomenon, whatever overlay that we provide, it ends up in failure. And how do we increase the longevity of this asphalt pavement that we provide? And that is that can be easily done by using geosynthetics. And here we see an example of an application of paver block, the paver fabric on the highway from Mumbai to Ahmedabad, and this is a typical crack pattern that we see on the roads because of several reasons. And on the right hand side you see the pavement, and this portion is treated with overlay fabric, whereas this portion is not treated when they have reconstructed this new pavement, and within a short time the portion that is not treated has ended up with the cracks, whereas the portion that was treated, it is perfectly fine, it is able to sustain its integrity. So that means that if we are able to use an overlay fabric, we can increase the longevity of our pavements, and this is how it works. Let us say that this is our granular base and we have the old overlay or old pavement which has a crack, and then on top of that we pour new asphalt to repair these cracks, and in no time this crack just simply propagates, resulting in the failure of the pavement. This is without any overlay fabric. And now let us say that at the interface of the old pavement and the new pavement we introduce some obstruction in the form of geotextile or a glass grid, or we have several varieties of products that we can use. And here in this particular example we see that they have used a geotextile that is saturated with the tack coat. And in one of the early lectures we have seen the property of the geotextiles that have binding with asphalt, and this particular one, this geotextile used is bitumen coated geotextile to prevent water movement and also to prevent the surface cracks from propagating. And this obstruction that we provide, it confuses the crack and it does not have the continuity to propagate. So, it requires much longer load repetitions before this crack propagates into the new overlay, and that means that our repaired pavement can function for a longer duration without failing. And another manner in which the performance increases is we can cut off the infiltration of the surface runoff, and that is one important factor that needs to be considered whenever we provide this overlay fabric. And the water is the culprit that causes failure in most of the soil structures. In 2009, Kodai et al. They have published a very nice paper summarizing the laboratory test results from their experiments, and they have done some laboratory tests by giving asphalt overlays that are reinforced with geogrid reinforcement, and purposely they have given a pre-existing crack of different widths, and they have rested this on top of a neoprene rubber layer to simulate our flexible base, and they have applied repeated loads to cause the failure, and this is how it is their experimental setup. And they have used two types of old pavements. One is a concrete block and the other is an asphalt pavement, and in this old pavement they have given a cut, and then they have provided this overlay, and with reinforcement or without reinforcement, and they have subjected this system to repeated loads with a pressure of 600 kilopascal loading. This 690 kilopascals corresponds to standard loading that we have under standard axial load and standard tire pressures. So, the result is something like this. This particular result is for the reinforced case over existing concrete block. This is the concrete block, and this is the start of the test when n is 0, and this is the crack that is there, and at 20% of the fatigue life is absolutely no cracks, and 40% no cracks, 60% no cracks, and then finally 100% there are some cracks, and this crack has propagated after 267,830 cycles of loading at a deflection of 3.9 millimeters. Whereas, if we compare the same thing for the unreinforced case, exactly the same, both are exactly similar, except that in the previous case we have given a reinforcement layer, whereas here it is not given, and within about 52,000 cycles the entire system has failed. We can see right at about 21,000 cycles there is a small crack that is initiated, and that is reflected from the bottom old pavement, and at 31,000 we can clearly see, and at 42,000 we can clearly see two of these cracks, and at 52,000 these cracks are fully formed, and at that stage the test is stopped. Whereas here even at 200,000 cycles the crack has not reached to the top, only at about 267,000 cycles the crack has reached the top. and this is how the data is looks like. On the x axis we have the number of cycles, and then the y axis we have the vertical crack growth, and when there is no reinforcement, immediately the crack propagates, whereas with the reinforcement at different levels, the crack propagates at a slower rate. That is, they have tested with by placing the reinforcement at 3 locations, at the bottom, then at the middle of the overlay, and then at bottom 1/3, and they have seen the best performance when the reinforcement is placed at the bottom 1/3. Is actually what happens is, when it is placed at the interface of the old pavement and the new overlay, the result was not very good. That means that there is a separation that is taking place between the old and the new pavement, and if it is placed at mid height, it is almost in the compression zone. Like we know that when we have a simply supported beam, the bottom fiber is subjected to tension and the top fiber is subjected to compression, and exactly at the neutral axis the strain is 0, and unless we provide reinforcement where there is a significant tensile strain, we may not get much of a benefit, and that is what they have seen. See, when the reinforcement is placed at the bottom of the overlay, there is not much of a benefit because there is a separation, whereas at mid height there is not too much benefit because this is more closer towards the neutral axis, but then if it is provided at 1/3 of the base height, it has the maximum benefit. That means that the reinforcement is able to hold the tensile cracks together, so that the pavement performs better. Here we see the data in the form of bar chart. This data is for 3 different crack widths: 10 millimeters, 15 millimeters and 20 millimeters, and obviously with the 20 mm initial crack width, the number of cycles to failure is lesser, and with the 10 mm crack width, the number of cycles is high. And there are 2 types of tests, that is, number 1 is the old concrete pavement and number 2 is the asphalt pavement, the old one. And when the reinforcement is provided at 1/3 depth, there is a good improvement, and bottom 1/3 is the best performance, and when there is no reinforcement, the number of cycles to failure is very low, and when it is at the bottom also the reinforcement benefit is low, and the same data published in a slightly different form. There is no reinforcement, and when the reinforcement is provided at the bottom and 1/3 and at mid height. So, this when the reinforcement is provided at 1/3 height from the bottom, it has the maximum benefit. So, this we see that when we place a reinforcement at bottom 1/3 of the new overlay, we can increase the longevity of the pavement. And these are some of the MORTH specifications for paver fabrics. This is the Ministry of Road Transport and Highways. The grab tensile strength should be of the order of 360 newtons, and the elongation, grab elongation is 50%. Then asphalt retention should be 10 kgs per square meter, and the melting point should be greater than 150 degrees centigrade, because the asphalt is placed at a very high temperature, and our geosynthetic, it should be stable at that temperature. And the separation function is something like this. Let us say that we have a soft subgrade, we have this aggregate layer, and unless we have a separator in the form of either a geotextile or a geogrid, and this aggregate from this layer gradually sinks in, and we may get an intermixing of the fines from the subgrade in the aggregate layer, and this may lead to piping failure, or the strength of this aggregate itself is impaired. And if we have a separator, we can increase the performance, because the strength of the aggregate is preserved for a much longer period. Then we prevent the piping, and that means that the strength of the subgrade is also preserved. And the same separation function is illustrated better here. This particular slide is from the International Geosynthetic Society website. Without a separator, the stone aggregate just slowly disappears into the soft subgrade, whereas if we have a geotextile layer or a geosynthetic layer as a separator, the integrity of this layer is preserved, and it stays for a much longer time. It provides a very good base for the pavement. And some of the specifications that are used as a separator are given in the AASHTO for 3 different classes of loading: class 1, class 2, class 3. The grab strength, when the strength is mobilized at a strain less than 50%, 1400 newtons. When the same strength is mobilized at a much larger strain, epsilon greater than 50%, we should have at least 900 newtons for class 1 type of loading. And then the puncture resistance, 500 newtons for a stiffer geogrid, and 350 newtons for a softer geogrid or a geotextile, where this puncture resistance is mobilized at a strain greater than 50%. And the TS strength, once again for epsilon less than 50% and epsilon greater than 50%, 350 and 500. So, these are just the guidelines that we can find in most of the standards, and depending on the particular application that we have to analyze and then properly choose a fabric that has good strength and good opening size, so that it can act as a separator and as a filter. And here we see the application of a thick geotextile as a drainage layer. Invariably, because of the cracks that are present in our road surface, the rainwater enters the pavement, and unless we lead the water safely away from the pavement, the rainwater may enter the subgrade. And to prevent the rainwater from entering the subgrade, we can provide a good drainage layer and lead the water into some side ditches or side drains. So, actually we will see this how to design the geotextile to serve as a drainage layer in some other lecture. And here we see the filtration function of a geotextile. Only the water should come out, and it should leave all the fine soil particles in the subgrade. That is, we do not want any piping failure to happen, because the piping is the loss of fines from the subgrade, leading to the loss of integrity and loss of strength. And this geotextile layer, it should have proper opening sizes consistent with the properties of the soil that we have at the site, and that once again we will discuss how to select a proper geotextile with having some appropriate opening sizes in some other class. So, how do we install the geosynthetic for our construction purposes? These are the steps. When we go to the site, we need to level and prepare the ground, and later we spread the geosynthetic, and we dump the aggregate, and then spread the aggregate, and then finally compact the aggregate by suitable means. These are the different steps. When we go to the site, we remove all the roots of the trees and stumps or large boulders, and if we have any low spots, we fill them and level the ground, and then on the prepared ground we stretch the geogrid or geotextile, and we should pin them down, because sometimes these geogrids may be so stiff that they have a memory, they just simply roll back. In that case we need to pin them down. And it is also very important that when we spread the geotextile or a geogrid, there should not be too many wrinkles, there should be some tension given, so that right from the initial loading itself the geosynthetic is subjected to tension. Unless some strain is developed in the geosynthetic, it will not be able to mobilize its tensile capacity, and if there are too many wrinkles, you need a very large rut depth to mobilize some tensile force. Okay. So, it is very important that when we install the geosynthetic, there should not be any wrinkles, and it should be tensioned as much as possible and pinned down before we do the actual other part of the construction. And whenever we have a curve, we can either achieve the curve by folding the fabric as indicated like this, and once you fold it, you pin it down so that we do not lose the curve, or we can use the cut pieces to achieve the curve like this. And once we lay the geosynthetic, we dump the aggregate, and it is very important that our dump trucks or the compaction vehicles do not directly travel on the geosynthetic, because if we directly travel, the geosynthetic may get damaged, and it is recommended that at least 150 to 300 millimeters cover is given between the truck tires and the geosynthetic in order to protect the integrity of the geosynthetic. And this is how it happens. We dump the aggregate and then spread it, and the spreading is usually done by some dozers like this. You just simply push the aggregate, and in this particular case we see the geocell reinforcement being used. We can spread the aggregate, and then final step is compaction, and usually we compact by using roller compactors, and for compacting aggregate materials like the granular materials, we use a vibro rollers. That is, not only we apply static force, but some vibration is achieved. And if we are dealing with clay soils, we have other type of rollers with a sheep's foot roller, and by using a suitable type of rolling equipment, we can achieve the compaction. And the quality of compaction is always monitored in terms of the Proctor density, against the Proctor density, and we achieve at least 95% Proctor density after compaction, and that is usually checked by doing the field density test, either by sand replacement methods or by using the nuclear density gauges. We can monitor the densities. So, thank you very much. That is a brief description of the design of the flexible pavements, and how we can use the geosynthetics and some aspects of the construction. Okay, thank you very much.